we started talking about collision theory. Okay? Oops, I try again. All right. Now, just to review briefly for those people who are not here. All right, what were the two things, two requirements to have? Yep. What were the two requirements for a successful collision? Sufficient energy and proper orientation. Okay? So we want to have successful collisions. The two requirements were to have proper orientation and enough energy. So one of the examples I used was talking about plugging in a cord in an outlet. If you try to plug something in and you go plug it in the first time, you might try to plug it in and the cords automatically go in. No, sometimes you go to plug it in and what happens? You could force it and sometimes it still won't go in. Have you ever tried to plug it in and you have to flip the cord over? Yeah. Okay. It's got to do with the hot slot and neutral slot and it not being lined up and you have to flip it over. One of the other examples I gave is if I put somebody up here blindfolded, jabbing at the outlet, trying to line up the cord with the outlet, are you going to hit it the first time? No. I dare say no. So some of you might be lucky, but molecules bang in and collide with each other constantly. If they don't have the right orientation or enough energy, are the collisions going to be successful? No. Very few collisions are successful. So when collisions are not successful, we need to give them more opportunities to be successful. So we talked about 5 factors to make collisions more successful. How can we increase our opportunities to be successful? What were the 5 things we could do? And these are all in the video. You can get the notes.
Regular successful collisions.
How can 2 requirements for successful collisions? Okay. What were the 5 factors to increase successful collisions? What were the 5 rate factors? Increased temperature. What was the other ones? Surface area. Catalyst. Add a catalyst will make it go faster. Increase concentration. And number 5 was the nature of reactants. So, where on the periodic table are things just naturally going to go faster? Group 17 and Group 1. Where are things just naturally going to go faster? Slower.
What is CO?
Concentration.
Wouldn't it be the
14?
Group 14 would be slower. Where else would it be slower?
15?
In the transition element. Now, those of you who are absent, this is all on the video.
Okay, but what is SA?
Surface area. Now, from there, we talked about activation energy. Okay? And activation energy is where I told you we were going today. All right? Activation energy was what? The minimum energy required to start a reaction. Now, from that, if it's the minimum energy required to start a reaction, I told you to think about this as like getting out of bed in the morning. Those of you who are easy to get out of bed, you're generally morning people, all right? You're going to require very little activation energy. Those reactions that are easy to start are like you. Those reactions that are hard to start require a lot of energy to get out of bed in the morning. Those are the reactions that are going to require a lot of activation energy. Now, the symbol that we're going to use for this, I told you Friday, is E with a little A on it, okay? Because energy is the universal symbol for E. We put a little A on it. Why we don't use capital A, E, I don't know, like kinetic energy is KE, but we use an E with a little A. Now, today, we're going to talk about how to start potential energy diagrams, because I'll be surprised if you don't see one of these on your exam somewhere. Now, potential energy diagrams show the activation energy and the heat lost or gained. And And that's going to have a name we're going to talk about very shortly. To start a reaction. I'll be here today during lunch, and I can probably stay till about 4 o'clock today. Okay. Today's the latest I can stay. Every other day I've got to be out of here pretty soon after the bell. But today I don't have to be in Thomasville until 6. Every other day I've got to be there by 5.
What was that quiz on? What was that quiz on?
It started at the beginning of the unit on solids, liquids, and gases and their definitions and properties, and it went through the beginning of equilibrium. And honestly, if you know it, you'd probably be better served getting it over today if you can, because the next opportunity I have other than lunch is next Monday. What lunch you got?
Third.
Yes.
Okay.
I can do third lunch any day this week.
Okay.
But I can't do after school any day but today. And even then, it's got to be done by 4. Say what?
Second lunch.
I really do not like to do second lunch.
So she's making exceptions.
Small exceptions. And it's not group.
What quiz?
Fridays.
We had a quiz?
Oh, what? When is it due?
So easy.
It's not due at any particular time. You can wait to take it until I set the cutoff for the quarter. The problem is, what happens is you wait. Darlene was my example I picked on the other day. What happens when you wait, Darlene? You just forget it. The longer you wait, the more you forget. It's multiple choice.
Well, I'm coming at lunch.
Okay?
Coming at lunch.
All right. So, a potential energy diagram. There are 2 kinds that you have to be able to read. Mainly because, what 2 types of heat reactions have we learned this semester?
Fusion. Vapor.
I need donations up here on my desk from my alpaca farm. I so need to get out of teaching.
Heat reaction.
What are the 2 types of heat reactions we've learned this semester?
Boiling point.
They start with E's.
Equilibrium.
Ectothermic, exothermic.
Oh.
Thank you. Endo and exothermic. So one of our potential energy diagrams is going to be endothermic, and one of them is going to be exothermic. All right? So on our graph, all right, energy is always on the y-axis. Now, it might just say energy. It might say potential energy. It depends on who the author of the graph is as to which way they label it. They might just say energy. They might say potential energy. Truthfully, they can do it either way. Now, the x-axis is the most bizarre because they can say like A plus B yields C. They can give you a real reaction with real elements in it. They can write something obscure like course of reaction. Okay? They could write reactants yields products, but they're going to say something about a reaction on the x-axis. Okay? And by real reaction, I mean they might say like KCl plus oxygen yields KClO3. But they're going to give you something about a reaction on your x-axis. Now, I've done this a long time. Now, the potential energy diagram is always going to be a graph that has a big hill in it. Now, because this reaction is always on the x-axis, and you always start with a reaction down here. What's always on the left side of the reaction? Somebody better start putting some money on my desk for some alpacas. What's on the left side again? The reactants. All right, so the reactants are always over here. All right, which I'm going to label R from now on. All right, the products are always at the end. Is she for real? I know I'm a fluffy white woman, but it had been cold in here all day. These fans are sucking all the air conditioning out of
I
here.
was moving and the heat, everybody's heat was running. But now
It's hot everywhere
I'm
else.
sitting
I'm
down
but
and the cold is hitting.
Well, the fans are sucking all the air conditioning out of the room. They suck the air out and recycle it every 20 minutes. All right? Now, from there, we have to learn how to find two things. Does everybody have what we need? All right. So we've already defined activation energy. So to find EA,
Don't call me that.
okay? This is found from the reactants to the top of the curve. Okay? From the reactants to the top of the curve. Now, we're also going to find EA reverse. That's called reverse activation energy.
Is that line supposed to be reversed?
Yep. Okay. Now, if we're reversing the reaction, where do you think we'd have to start to be at the reverse of the reaction?
The product.
Okay. So you're going to start at the products and go to where?
The curve.
Top of the curve. Okay. So activation energy, if we go forward, starts at the reactants and goes to the top of the curve. If you're finding EA reverse, you go from the products to the top of the curve.
What does reverse EA mean?
Reverse activation energy just means the activation energy to start from the reverse side of the reaction. Still the minimum energy to start the reaction, it's just the reverse. It's the exact same thing. It's just the reverse reaction. Does everybody have what they need off the board? Because we need to label it on the graph. Because you're going to have to find these on a graph with numbers and without numbers. So what?
You say our quiz on Thursday?
Yep.
What's on?
You will see these on the graph.
How many questions?
I don't know yet. Haven't decided if it's going to be for response multiple choice again.
Okay, see, no.
Get away, get away car.
This tennis ball came out.
Then put it back on.
That was true.
All right. So if we go to the graph, all right, can we all agree that the reactants are here? So if I draw a line across, not very good line, let's try that again. All right, here are the reactants, right? From the reactants to the top of the curve, that is EA. From the reactants to the top of the curve is EA. Now, EA reverse would have to go from where? The products. So let me draw a line from here. All right, so here are the products. So if I want to do EA reverse, I have to go from the products to the top of the curve. That's EA reverse. Right? So which one requires less energy, the forward reaction or the reverse reaction? The forward reaction. It's much easier to go the forward way. Reverse reaction, that's a heck of a hill.
Did it start at the bottom?
Hmm?
Did the potential energy start at the bottom?
What, down here?
Yeah.
Nah. Okay. Now, the last thing we have to find on this is a new vocabulary word for us that we're going to use tomorrow too. It's called enthalpy. Enthalpy is delta H. It means heat content. Okay? Enthalpy means heat content. Now, there's two types of enthalpies we're going to have. You know how we've been calculating Q and we just did Q on the lab? It was never negative, and I kept telling you it was always positive. That's because Q is not negative. This is where our negative numbers come in. If delta H is a negative number, it means we have an exothermic reaction.
The other one was endothermic.
Yep. If delta H is positive, we know it's endothermic.
What if it equals 0?
It's not going to. Now, we can have something called Gibbs free energy that we're going to talk about tomorrow. That can equal 0, and it will be at equilibrium. And we're not going to do that either because in the curriculum, believe it or not, they don't want us to calculate it, which would be so much easier. They just want us to talk about it conceptually. So it's either going to be positive or negative. I don't know why they don't want us to calculate it. It's kind of dumb. All right. Does everybody have it?
I don't know.
I do.
Why do you have chemistry textbooks? I don't know about it. You ain't never used it.
Well, I've had those since, best guess, 98, 99. We'll do my best guess.
When's the last time you used it?
The white ones are chemistry 2 books. The red ones are first year.
We have chemistry 2 here.
We've taught it a few times.
What?
I probably haven't
College now?
taught chemistry 2 in 3 years. All right. Wrong way. So, how do we find delta H? Where do you think delta H would fit on this graph? First of all, see if we can answer this. Is this reaction endo or exothermic? How do you think we figure it out?
If it goes up or down.
Let me ask you this. Or I ask that again. Is heat absorbed or released on exothermic? Okay, it's released. So that means endo is absorbed. All right. Think about those words. Okay. And now look at this and see if you can tell me.
It's endo.
Okay. Why is it endo?
Less energy. That means it's absorbed. It's cold.
Which one did she say?
All right. You said it has less energy. I like that part. It does have less energy. So that means what?
Excellent.
Okay. Products are lower energy or heat is lost. So if energy or heat is lost, what kind is it? It's exothermic. Means it's exothermic. Okay? It means it's released. So I asked that. Most people can figure that out looking at the graph. Okay? The products are lower, which means energy or heat is lost. It's an exothermic graph. Right. They're never going to be the same, which is why I said you wouldn't get 0. Okay? They're not going to be equal. Now, how are we going to find delta H on the graph? Can I turn? Because I want to label how we find this. All right. So how are we going to find this on the graph? Delta H is the difference between the reactants and the products. Okay? Delta H is the difference between the reactants and the products. The difference between the reactants and the products. All right, we caught up? So if I go back to the graph, all right, where are the products?
On the right.
All right. And when the reactants are here, right? So the difference between here And here is delta H. So is delta H here going to be positive or is it going to be negative? How'd you know it was negative? And you told me it was what kind of reaction?
So.
You told me it was exo. That's how we know it's negative. Okay? Now, let me ask you this. The reverse reaction. Delta H reverse will be what then? It will be positive. Will the numbers be the same or will they be different?
Different.
Same.
Numbers will be the same. The only difference is the what?
Signs.
The signs. The signs will be different, but the numbers will be the same. Because it's still going to be the reactants to the what? To the products. That's not going to change. Now, tomorrow, we're going to practice this with numbers. Now, what's the difference between this one, which is exo, and endothermic?
The product is gonna end up higher.
The products are going to end up higher. So if I draw endo real quick, let's just say I write A plus B yields C, and I write potential energy there, except I fixed that. It would just look like this. That would be endothermic. Okay? Everybody see the difference? Okay? These would be the reactants, and those would be the products. And the products are higher. Does everybody see the difference on endo where the products are higher? Could you identify that if they put it on the exam, or I put it on something and ask which one's endo and which one's exo? Yes? I wouldn't get a whole bunch of wrong answers and feel like I need to become an alpaca farmer.
But if it's EA reverse, if it's EA reverse, it's exo.
Huh?
If it's EA reverse on it's exo.
Mm-hmm. All right, so what's our homework tonight?
Well,
Study.